right. So the last part of chapter 19 is focusing on two new reactions. The first one is nucleophilic aromatic substitution. This is very different than the reactions we've been seeing, but you still end up with a new substituent coming off of your benzene ring. So let's take a look at an example, and this will put it all into context. With nucleophilic aromatic substitution, we always have to have a leaving group on our molecule. So I'm going to circle this, and bromine in this case is going to be our leaving group. The other thing that you must have in order for a nucleophilic aromatic substitution to occur is a nitro group or something else that is really electron withdrawing. And in this reaction, what we're going to do is we're going to treat this with a strong nucleophile. So I'm just going to choose hydroxide. And then in the second step, we're going to treat this with acid. The product that's observed when you run this reaction is going to be a phenol. So now the question is, how the heck does this mechanism work? So let's take a look at the mechanism for this reaction. And before we even start the mechanism, I want us to determine what carbons on the ring are electron rich or electron poor. So if we're looking at our starting material, which carbons do you think are electron rich or electron poor? Yeah, remember the nitro group's very strongly electron withdrawing, so we've got a delta positive right here, here, and here, right? Those are very, very electron withdrawing carbons. If we have hydroxide in solution, that means hydroxide's now going to act as the nucleophile. The benzene ring is not going to be nucleophilic. In fact, the benzene ring in this case will be our electrophile. So it's a little bit flipped from what we saw in our previous examples, and the hydroxide will be our nucleophile. Our nucleophile in this case is going to attack one of these delta positive carbons.
So there's a really partial negative?
Partial positive.
Yeah, that's it.
Does it look like a negative? Yeah, sorry. These are all partial positives. So the nucleophile will attack one of those partial positive carbons. And then we have this funky looking intermediate where we've got OH, we've got Br. Oop, I forgot one arrow too. We can't have a Texas carbon, so we'll push some electrons over. And I'm actually going to draw out our full nitro group as well. This is known as a Meisenheimer complex, so I'll even write that down. So the sigma complex is where you have a positive charge in your aromatic ring, and Meisenheimer complex is where you have a negative charge on what used to be an aromatic ring. Apparently you get to name something after yourself if you find something like that. All right, let's draw the resonance structure. Or major resonance structure, I should say. Well, we know we can push these electrons down. Then what? Then we can push them down over here. And then we can push this down over here. So let's draw this resonance structure. Oops, this should be a single bond. All right, if we look at these, which one do you think will be our major resonance contributor? The one on the right or the left? the right. So if we look at the one on the left, it has a negative charge on a carbon. Carbon's not that electronegative. The one on the right has the negative charge delocalized all the way to the oxygen. The oxygen's a lot more stable with the negative charge. So this is our Meisenheimer complex. The cool thing with this is that it will quickly rearrange because it's not happy not being aromatic. This negative charge will hop down, this will hop down, this will hop over, and we'll eject off this leaving group over there. And then we end up with our final product. Typically, this reaction's run in an excess of base. So what do you think might happen next? Deprotonate. If you remember, phenols typically have a pKa of around 10. Do you think this is going to be more acidic or less acidic than a normal phenol? What do you guys think with that nitro group on there? Much more acidic. You've got a very strongly electron withdrawing group on there. So in this case, this phenol is very acidic. So that if you do have excess hydroxide, it will actually continue to go on and to deprotonate your phenol. Got O minus, got NO2. This is a really stable conjugate base because that negative charge can actually delocalize all the way into the nitro group. So this is incredibly stable, which is why the last step in this reaction usually involves some sort of reacidification. So we break this up into two steps. First step, we treat it with strong hydroxide under pretty high temperature conditions usually. And then second step, we reprotonate it in order to isolate our alcohol. Does that make sense? It's a little bit different. It's flip-flopping our nucleophile and electrophile. So let's make a brief list of criteria for... Yep?
Why do we just do the second part over when we have the product already?
So the problem is in this first step, we're treating it usually with a huge excess of hydroxide. So we'll run into a problem of accidentally deprotonating our product. And so we have a separate step at the end to reprotonate it. So let's make a list of our three main criteria. First thing is you must have a strong deactivator. Second thing is your deactivator must be ortho or para. To your leaving group. And then the third thing is you obviously have to have a leaving group. Specifically, you must have a good leaving group. What are some common good leaving groups we can use? I showed you guys one. Halides, right? So things like bromine or iodine are good leaving groups. What's another good leaving group? Well, if we're doing it under basic conditions, we can't use water anymore, right? How can we turn an alcohol into a good leaving group? Tosylate it, right? So we can use halides or tosylates. These are the most common that you'll see. The one small thing is you can't use fluorine as your halide. Why is that? It's a crummy leaving group, right? So the halides have to usually be at the bare minimum chlorine. You can't go all the way to fluorine. All right, we have one last reaction for chapter 19. This one's similar. This is called elimination addition. So let's take a look at an example here. Let's say I've got bromobenzene and I want to do nucleophilic aromatic substitution. So I'm going to treat this with a strong base. And then step 2, I'm going to reacidify it with acid. Will this work? Will we get it to substitute that bromine for an alcohol? No. Yeah, we don't have a deactivator. So no reaction because we have no deactivator. So in this case, nucleophilic aromatic substitution won't work. However, chemists are stubborn people. What do you do if a reaction won't work? You try it again and freak out. If your reaction's being sluggish, what's the simple solution? You heat it up. So they did this and they found you can take sodium hydroxide, heat. You have to heat this up really hot. H3O plus. And you get an alcohol installed. Pretty strange reaction. People for a good portion of, I think like the 1940s, had no idea why this reaction worked. They just knew it worked. You'd have to crank up the heat to like 150 degrees, but eventually it would work. And yeah, people are like, well, just roll with it. Until some studies came along, and they were able to elucidate the reaction mechanism. And the mechanism's pretty strange. Oops. So we've got bromobenzene, and we've got hydroxide. Hydroxide's a good nucleophile, but it's also a pretty good base, right? So if we look at this, we've got a beta proton next to a leaving group, right? So our base could come, grab this beta proton, clamp down, and kick off our leaving group. And if you guys remember from the practice exam from last term, we run into this really strange intermediate. What's this called? What was it? Benzyne. A lot of people look at this and say, how the heck do you get a triple bond in a ring system? That's not even close to 180 degrees. The reality is it's not a true triple bond. Benzyne can oftentimes be thought of as a diradical, where one of these carbons has one electron and the other carbon has another electron. So it's kind of in between a diradical and a triple bond, but it's very, very reactive. It's not happy being benzyne. All right? So now that we've formed our benzyne, we have more hydroxide floating around in solution. This hydroxide can actually attack one of these carbons and then kick over electron density to the adjacent carbon on our benzyne. So now we've got OH, got a negative charge over here. Oops, and we've got this pi bond. The last step is this proton will be abstracted from the hydronium, and we'll have our happy phenol. I feel like that painter on PBS. Draw some happy phenols. This is an incredibly weird reaction. Does anybody have an idea of how they proved this reaction? There's a couple different things. So maybe mass spec. Yeah, I mean, they knew they made the phenol, but the question is, how do you think they proved that they made a benzyne?
Guessing.
It's pretty weird. So I'll show you guys this.
Does it smell bad?
So benzyne is incredibly unstable. You only make a tiny amount. So I'm just going to write mechanism details. This is how they came up with some information regarding the mechanism. let's say you run this reaction and you treat this with something like furan. What do you think will happen? Diels-Alder. So they actually checked this reaction to see if it would do a Diels-Alder. Somebody proposed maybe this goes through a benzyne intermediate. Somebody else said, well, if it goes through a benzyne intermediate, it should do a Diels-Alder reaction, because we know alkynes like to do Diels-Alder reactions. So if we go through and we look at this pi bond will hop over, this pi bond will hop over, and then this pi bond will hop over. Oops. Let me keep the double bonds in the right positions. And you end up with this bridgehead where there's an oxygen in the top. So there's a lot of experimental evidence that this does go through a benzyne reaction. So I'll just keep this as a side note. Typically, this reaction's done slightly differently now. Typically, it's done with sodium amide. So NaNH2. The reason behind this is sodium amide's a much, much stronger base, and so you don't have to crank up the temperature and cook your materials as much. So we'll write lower temps. So let's take a look at this reaction with sodium amide. And I'm actually going to change our functional groups here. When they run this reaction with sodium amide, the solvent is ammonia. So let's go through and try to figure out what's going on with this reaction. We know we've got these beta protons. Doesn't really matter which one we pick. I'm just going to pick this one. We're going to clamp down. We're going to kick off our bromine. And now if we think about it, we've got some more, some more sodium amide. So I'm going to write, Na plus, NH2 minus. Which carbon on the benzyne do you think will be attacked, or do you think it really matters? Do you think there's a preference in terms of regiochemistry for internal alkynes? Not really. So another interesting observation with this reaction is you'll get some of it attacking here and kicking electrons over. If you do this, you get NH2. You'll get a negative charge there, and CH3. Or the alternate pathway involves attack at the other carbon. Nope, this is not a regioselective reaction. So in this bottom one, we could have the NH2 attack that bottom carbon and kick up electrons over here. Oops. This is more evidence that it goes through a benzyne intermediate and not a true substitution reaction. So you lose regiochemical control, and oftentimes you get a mixture of products after this. Then the last step, we're just going to protonate this with ammonia, which is a very weak base. Get this proton to kick over. Same thing's true for down here. let me slide this over. We'll get our final products. Oops, forgot my double bond. All right, so that's elimination addition, or addition elimination, I should say. Yep.
Both those intermediates are aromatic.
That's a good question. So if we think about that, do you think the lone pair is going to be in the p orbital or in an sp2 lobe?
Well, I say they're aromatic, but they have supposed to be a pi bond, right?
Oh, shoot. Thank you. Good catch. I forgot my pi bond in there.
But it's not aromatic. It has
Well, let's think about that. Do you guys think this intermediate with the negative charge will be aromatic, anti-aromatic, non-aromatic? Oh, yeah, that negative charge is actually going to be located in an sp2 lobe. So the lone pair isn't counted towards the 4n plus 2 rule because it's not aligned in the p orbitals anymore. So we are going through an aromatic intermediate. Yeah. All right, let's continue on to a little bit of practice stuff. I've got some chapter summary information, and then we'll do a few practice problems. So like I said, just as with last term, really try to utilize the end of the chapter sections in the Klein textbook and try to do as many practice problems as possible. It will help you a lot. Try to make flashcards, make add-ons to your reaction maps, things like that. Whatever works for you, try to stick with it. Yep.
Is there a whited out version?
I can make you a whited out version if you want. Yeah, I'll make a fill in the blank one. So we've got all the reaction summaries here. The first section of chapter 19 was all electrophilic aromatic substitution, where the benzene was acting as a nucleophile and we were attacking strong electrophiles. And then recently we talked about nucleophilic aromatic substitution, where the benzene ring is now acting as the electrophile and you're using a strong nucleophile. And then we saw elimination addition. And we said that you can do this with hydroxide. However, it requires temperatures upwards of 350 degrees. It's not common. Typically, you see this with sodium amide, but like I said, you lose regiochemical control.
Was it temperature change for the leaving group or the elimination addition?
Yeah, if you had a better leaving group, you might be able to drop the temperature a little bit. Yep.
The two with the elimination, the orbital pair, it's just racemic, right? There's no.
That's a good question. It wouldn't be racemic because there's no optical activity, so we wouldn't define it as that, but you would maybe end up with a 50-50 mixture. I'm not positive on that. Yeah, that's a good question, though.
Is there any way to favor one over the other, or we just have to live with it?
Not really. You just kind of have to live with it. It's just an unusual reaction. That's a good question, though. So if we did want to install the aniline, though, and we could start from bare bones materials, we could install a nitro group and reduce it and form an aniline. So there's kind of roundabout ways to install amino groups. So on Monday, we'll practice some stuff like that. There's a decision-making tree, too, that's pretty useful. The first question you always ask yourself is, are the reagents nucleophilic or electrophilic? If they're electrophilic, it's always going to be that electrophilic aromatic substitution. If it's nucleophilic, you have to ask yourself whether or not we met those three criteria with the electron withdrawing group in the ortho-para position. If it is, then that's nucleophilic aromatic substitution. If not, then it's elimination addition. I've got the list of activators and deactivators here, which is pretty helpful, but it's pretty intuitive for the most part. What I want to do with the remainder of the class period is look at a couple of odd problems. And I want you guys to work with your neighbors to try to figure this out. First problem. Involves furan. Is furan aromatic? Yeah. How many electrons are in the ring system? 6. Why don't we count both lone pairs? Yeah, one's in the sp2 lobe. We only count one lone pair as a part of the pi system. So this can also do all of the reactivity that we saw this chapter. So I'm going to give you guys one reaction. And I want you to determine the product. This one's a little bit tricky. So let's consider the positions here. The oxygen's position 1, this carbon's position 2, then we've got 3, 4, and 5. Do you think we'll get the bromine installed at the 1 position, 2 position, or 3 position? So what I would recommend doing is try to draw out your reaction mechanism for this and then discuss with your neighbor which substitution is most likely going to occur. Yeah, don't worry about it. I would do both reaction mechanisms. Do you think it'll occur at position 1? Oxygen doesn't want to have a thermal charge. So the question is now between position 2 and 3. So have the electrophilic effect occur at position 2 or position 3, and then compare your intermediates, kind of like we did with the pot. So I'm going to help you guys out a little bit with the mechanisms, at least get us started. For the first one, we know the carbon could attack right here. And it would result in this carbocation. Well, let's compare. We could have one where it attacks using that bottom carbon. Shoot. We've got the carbocation here. We've got the bromine here. So we've got two possible reaction pathways that we need to compare. What do you guys think? So I heard some people say the first one. So you guys think the top one is? Why? Oh, more resonance, right? When you're ever in doubt in organic chemistry, the answer is resonance. So let's draw the resonance structures for this. Right, so we could move this over. Are there any more resonance structures? Yeah, definitely. One more. So we could move this lone pair down. Now we've got H and Br over here. We've got our negative charge, or sorry, our positive charge up on the oxygen. Let's do the same resonance delocalization for the bottom one. We can move this pi bond, or the lone pair down. We've got hydrogen, we've got bromine. Now this oxygen has a positive charge. Are there any more? No. So if we look at these two reactions, this top one goes through the more stable intermediate. So if we think about this, the top reaction is much, much more likely than the bottom reaction, right? So let's go in and we'll fill in our desired product, and then I'll give you guys another challenge problem. For this one, we know that the bromine's most likely going to occur in the 2 position. In fact, it's exclusively in the 2 position. You guys ready for the next challenge? We'll do pyridine. So another aromatic compound. The lone pair on the nitrogen is not included in the pi system. It's stuck in the sp2 orbital because the pi bond's already occupied. So the question now is, will the bromination occur in the 1, 2, 3, or 4 position, or some combo of all of them? I would recommend using the same strategy that we used for furan. Draw out all possible mechanisms and then kind of analyze them. I was going to make this an exam question, but I decided to make it an in-class problem. You guys can talk one minute. I'll get us started on the mechanisms here. It will usually attach to the carbon. So try to determine whether or not it'll be 2, 3, or 4 that gets the bromine. Oh, let me move these double bonds so they match. All right, so I've drawn the sigma complex for all 3 of these reactions. Right, so the top one we attacked using that bottom carbon, the next one we attacked, using this top carbon, and then this one we attacked using the very top carbon. Which one of these do you think is most stable? A, B, or C, or are you just guessing? Does anybody have an explanation? You think C? Okay, so let's go through and draw the resonance structures for these. I know it's a pain, but let's do it. All right, the top one, if we look at it, we could delocalize this charge. We could say, well, this charge could pop over, right? I'd put this positive charge over here. We'd have Br and H over there. We can keep on moving this. We could say, all right, whoops, this charge could hop over. Right? Or am I doing this right? 1, 2. There we go. We've got Br and we've got H. What's the charge on that nitrogen? Positive, right? All right, let's do the same thing for the next one really quick. We've got this, we've got this pi bond that could hop over here. Shoot, let me think about this for a second. There we go. I'm having a brain fart today. So if we do this, we've got a positive charge right here. We can keep on delocalizing this. Pull this pi bond down. Yep, they're aligned p orbitals, right? So we've got H, we've got Br, now we've got this and this. We've got a positive charge right there. So in both of these, we can actually move the charge around the ring. Which one do you think is going to be more favorable, the top one or the middle one? Ah, they both have 3 resonance structures.
Yeah, but the top one has the positive charge on nitrogen.
Top one has a positive charge on a nitrogen. Does a nitrogen want a positive charge?
No, they can handle it better.
Not as much. If we look at the bottom one, it has all the positive charges on carbons. The top one has partial positive character on an electronegative atom, meaning nitrogen. In this case, this one is actually slightly more stable. Simply because this top one has this positive charge on this nitrogen. That's a really unfavorable resonance structure. So that'd be an ultra minor contributor. So in this case, we actually get bromination occurring primarily at the 3 position. The 4 position is pretty similar to the 2 position, and it has similar resonance structures. All right, Monday we'll do synthesis practice. Make sure that you do the sapling problems. Make sure you do those.